lack of geometric proof in a little bit. Okay. But I'm pretty sure the end result is correct. So let's go ahead and extremize it first. You cannot have too many infinitesimals also. Right? That's the other thing. No, that's okay. Yeah, it should be d squared, dr times d theta. That's okay. But okay. Anyway, so as the prescription goes, well, let's write it down first. Right? So the total, the area itself is given by what I just wrote down, integral from 0 to 2 pi, and then the dA, dA is that guy, so I have to integrate it to get the area. But I also have a constraint, which is that the total length must give me L, right? So this L is fixed. So what's the total length? It's just, since we know our differential geometry, it's just this guy here, okay? And that in fact means this is actually just from 0 to 2 pi, and this is in fact just R prime r dr d theta squared square root d theta integrated over from 0 to 2 pi. Okay, and so this is the constraint. This is the thing we want to maximize. So as the prescription goes, what we do is we form the total action, which is now 0 to 2 pi of d theta. But we now need to take our original Lagrangian and then superpose it over your constraints and then multiply by Lagrange multipliers. In this case, there's only one constraint, so there's only one lambda. And again, because it's a global constraint, there's no time dependence in this lambda. Right? Times this integral over here, square root of x prime squared plus y prime squared. Okay. This guy, by the way, you can also look out. It's just a cross product, right? So this is x prime, x, y, and then 0 cross with x prime, y prime, 0, right? Because we're on the xy plane. I'm just using the cross product for convenience. And so this will turn out to be 1/2 x y prime minus y x prime. Okay, and then in fact, let me just write down. So the total Lagrangian is therefore 1/2 of this minus capital lambda, which is a constant, times the square root of x prime squared plus y prime squared. Okay. And so now we can go ahead and apply Euler-Lagrange. Euler-Lagrange, there are now two sets of equations because there's x and y. So let's do x first. x looks like this, right? So there's dd theta, and then dd x prime acting on these guys. So uh, so we have this guy minus dl dx, and this is all 0. Okay, and so total Lagrange. So let's work it out explicitly. The x prime derivative of L is minus y over 2, and then you take a theta derivative, so that's y prime. So again, you take this derivative, and then you take the derivative with respect to theta. So this becomes minus y prime over 2, and then minus lambda, and then dd theta acting on x prime over square root of x prime squared plus y prime squared. Okay, and all of that is 0. And then likewise, I can do it for the y. Okay, so I got dd theta, and then dl total dy prime minus dl t dy. I'm sorry, I haven't done this one, have I? So this one is minus the derivative of x, so it's actually, the only thing relevant is this guy, so it's actually minus y prime over 2. Okay. So meaning now we can say this is actually y prime minus y prime minus lambda, and then dd theta, all acting on x prime over square root of x prime squared plus y prime squared. Okay. And likewise for the y calculation, something similar happens, right? But let's do it as well. So again, you differentiate with respect to y prime first, which now involves this guy, and then you take the derivative with respect to theta. So this goes away, you get x over 2, and then you take the derivative, so you get x prime over 2 minus lambda, and then dd theta with now the derivative with respect to y prime, so this will give you y prime over square root of x prime squared plus y prime squared. Okay. Minus dl dy, and that gives me this guy here. Right? So minus plus, actually now plus, because minus gives you plus, and then it's x prime over 2, which means now you have x prime minus lambda dd theta y prime over square root of x prime squared plus y prime squared. Okay. And now we can combine these equations. So first we integrate them one time, right? Because you see that everybody is 0, but let's package it nicely first, and then you can see. And let me not erase this, just to remind myself I have not justified the geometry yet. But here, what do we have? We have the following. Yeah, so we have. In fact, let me follow my own notes and. move this guy to the left hand side. So you got dy d theta equals to d theta minus lambda y prime, x prime, over square root of x prime squared plus y prime squared. Okay. And then for this guy we have now minus dux d theta equals to, in fact, let me erase the minus signs, right? Because if I move this to the left hand side, I get a minus, but there's a minus here. So it's now d theta of lambda y prime over square root of x prime squared plus y prime squared. Okay. So in other words, they are both total derivatives with respect to theta, which means that I can immediately integrate them. Okay. So when you integrate both sides, you get an integration constant. So all I'm going to do is I'm going to call it x naught and y naught. Right? So if I integrate both sides, I get a constant, x plus constant, and then here I also get a constant. So I can move all the constants together, package it together, and call it, for example, in this case, x minus x naught equals to lambda y prime over square root of x prime squared plus y prime squared. And then likewise, I can integrate both sides, and I get y plus constant, and then this guy plus another constant. Again, I can package it all together and call it y minus y naught. And then we get minus lambda x prime over square root of x prime squared plus y prime squared. Okay. And then now, we are in business. Why are we in business? Because now I can actually just square both sides and sum them. Okay, so what do I get? I get x squared, x minus x naught squared from here, plus y minus y naught squared, okay, from here. And so then therefore I must add the same squares from both sides. So I get lambda squared times y prime squared over x prime squared plus y prime squared plus lambda squared x prime squared over x prime squared plus y prime squared. Okay, and then I get 1, and then I get lambda equals to lambda squared. And so therefore, this plus this equals to a constant. What do we have? We have a circle centered at x, y, x naught, y naught. So of course we're not quite done yet in the sense that we have not quite figured out what is lambda, right? But what you will discover is that in this case the interpretation is very clear, because lambda shows up explicitly in the solution of our shape, right? So this is a circle centered of x naught, y naught, with radius lambda. Okay, but the constraint is the following: we want the total length, which means the perimeter, to be L. So if you know that's the radius, that means 2 pi lambda is in fact L, which means lambda itself is L over 2 pi. Okay, and so this in fact tells you that there is in fact, and it's often the case, the Lagrange multiplier usually has a physical or geometrical meaning if you're solving a physical or geometrical problem, a constraint problem like that. And so in this case, you can see it's directly related to the geometry, namely the radius. And in fact, we can go further, right? So I claim that this is a maximum area because of this constraint. And so you can test what I'm saying here by explicitly expanding the action, the total action, up to second order. Okay, so and you can check if this is in fact a maximum, then you should find that the second order variation of the action should be negative. So here I was told the last time that there's a sign problem with my notes. Maybe Lee can help me check at some point, but I'll check it again if you have some time to. This is problem 8.11 in my notes. I believe I did assign it for homework, but anyway, I'm going to try to check it myself as well. But I thought it should work out. I thought my answer should be correct, but I think both Jia En and Wei Hao told me they got a sign flip somehow. But if it is maximum area, the second order variation should in fact be negative, right? Because all variations should give a slightly smaller area. Otherwise, this wouldn't be maximum. So you guys will, in your homework, check it out for yourself. Right? So you take the circle, the solution, but then go ahead and perturb around that circle and plug it back into this action. And so what you will discover is that to zeroth order, you will discover that, of course, you get some number. First order will always be 0. So you should think about why first order should always be 0. Okay. In fact, I discussed this before. But first order, you always find that 0. And then the first non-trivial order is the second order. And like I said, it better come out to be negative. Otherwise, you don't have a maximum area. Okay. Any questions for me at this point? 这么快就跑掉了，听一听就不高兴就跑掉了。I'm just kidding. It's okay. Not happy. You're not happy that the circle maximizes the area. Is that what happened? That's why she ran away. Maybe it should be a square or rectangle. Yeah, it'll make her a bit happier. Anyway, I'm just kidding. So try it out and see for yourself that in fact it does maximize the area. So it turns out that this is the beginning, and that's why this is an interesting problem that I found from Byron and Fulmer. So it turns out to be an interesting introduction to what is called the reciprocity relation. So let me briefly mention what this is about. So yeah, again, I'm not going to erase this because I'm going to try to make sure I get the geometry right. I think it's because it's an infinitesimal slice, so you can get away with calling that one of those guys a plate, because it's infinitesimal. Okay. Yeah, so probably that's it actually. So yeah, let me actually come back to this problem, right? Because every time I see something wrong, I feel very uncomfortable. So r times d sine theta clearly is the height. That's just trigonometry. This guy here is clearly r times at up to first order in the infinitesimals. R times d theta. I say that because actually this is not quite r, but this is some r plus some correction, right? But it's okay because it's first order. I just want it to be accurate the first order. So whether I use this guy or use this guy, but in fact this guy itself, the height itself is basically, this guy and this guy are basically almost the same as well. Exactly because it's infinitesimal. And the justification for this is because this angle is very small. So of course, in principle, you need to do your trigonometry and figure out what this angle is. But whatever it is, because this is small, it's very close to 90. Okay? It has to be very close to 90. And so I claim that the height is basically dr, right? Which is actually r, which is, yeah. So this is the height. This is the height. Okay, which is dr, and this is also basically almost the same as dr. I think that basically is it. So really we do have an area of a triangle, and that's how we are able to find, once you know the dA of one slice, one triangular slice, then you just have to sum over the entire area. All the slices, I mean, to find the entire area. And that's why it's useful to use the angle, because then you can you know what the correct parameterization is. Yeah. Okay, so like I alluded to, and now I can erase that part. This begins a kind of introduction into something called a reciprocity relation. And in fact, the next problem after this maximum area tells you to solve a related but different problem, which is what happened. So previously, we just solved the following problem. Yeah? We say one maximum area, but fixed perimeter. But what happens if we flip it around? What happens when we flip it around? Meaning fixed area, but try to maximize the perimeter, or at least try to extremize it. Okay. So what you notice is the following. How do you solve this problem? So let me call this A and this is B. Right? For the previous problem, we set up things in the following way. It comes down to saying S total is some integral over the angle, and then you have your area integral minus Lagrange multiplier times the perimeter integral. Integrand, I should call it Lagrangian. Maybe to make it more clear, let me call it Lagrangian involving area, and this is Lagrangian involving the perimeter. Okay, and then in this case, I'm calling this guy fixed, the integral of this guy fixed. So therefore, this is the Lagrange multiplier. But in the second case, what you will end up doing is you will end up saying that, well, now they swap places, right? I want to now extremize this guy, but otherwise the same expression, but now is the area that I want to hold fixed. Minus, but so therefore now the Lagrange multiplier appears over here. You didn't like the fact that circles maximize area? Is that why you ran out and it's okay. Okay, I know, it's okay. Yeah. 就突然间跑出去，我以为你不喜欢圆 how do you say circle? You don't like circles. You don't like circles maximizing areas. And then you know this conclusion is just too outrageous for you. Is that what happened? And then you just ran away. I'm just kidding. Okay. So what you see is that there's actually a lot of similarity between the two guys, right? And so what you discover is that in fact they are related, right? So what I mean by that is that actions are invariant up to a constant, right? So for example, I can always pull this out. I can always pull out the lambda, and then I can go in this way, right? I can now have LP minus lambda LA, and this will now look exactly like this guy. For example, right? So the Euler-Lagrange equations for one thing are exactly the same thing. Of course, the constraints are different, but still, in fact, there is something called a reciprocity relation. So what you will discover is the following. So what you discover is that, in fact, the solutions are related. Okay? So you will discover homework. You will discover the solutions to A and B are the same. Maybe I shouldn't say same is a bit too strong because the Lagrange multipliers are not the same. So let me just say the solutions to A and B are almost the same. Okay. In other words, extremizing the area fixing the perimeter is basically equivalent to maximizing the perimeter and then constraining the area. Okay. But anyway, I'll let you guys discover this. I've given quite a bit away already. The Euler-Lagrange equations, as you can see, are basically the same thing. I'm sorry, I didn't get the. I obviously didn't get this right. So this is 1 over lambda. That's right. The Lagrange multipliers are not the same, but otherwise the problem is actually very, very similar. Okay, I think we should take a break, and then we'll come back and do another example. This time involving statistics, and then we should move on to do some Lagrangian mechanics. So my plan is I'm going to do a little bit of Lagrangian mechanics for 2 reasons. I hope you've seen it before, but the 2 reasons are the following. One is that I want to take this opportunity to discuss the Noether's theorem, right? The implication that whenever there are continuous symmetries in the problem, there will be corresponding conserved quantities, right? So what is energy conservation? Energy conservation is the conservation law that you get as a result of time translation symmetry. Meaning, if you do your experiment today, it should give you the same result if you do the same experiment tomorrow, or 1,000 years later, or 1,000 years before, earlier. So that's the statement about time translation symmetry. The space translation symmetry, on the other hand, gives you momentum conservation. Right? So it should not matter whether if I do my experiment here at NCU or if I do my experiment in Tsinghua. Somehow, space should not be different, right? Here or there, or back in Singapore or or in the U.S. So it would be very strange somehow if the experiments turn out differently. So that statement ends up giving you the conservation of momentum and so forth. So that actually this gets very sophisticated. Actually, even fundamental physics is filled with examples like that. Right? It's just a question of what are the symmetries, and that's the part that gets more sophisticated, gets more and more mathematically abstract, gauge symmetries and so on. That's why I want to talk about it. The other reason for it is because of constraints. So as I've said before, today what we're talking about are global or integral constraints, right? You integrate and get a perimeter, or you integrate and you get an area, and that total integral is constrained to be some fixed number. But for Lagrangian mechanics, as you know, probably you guys have done it before, in fact, right? So, for example, you can put a particle on a bead, and a bead on a particle on a ring, and you make sure that it can't go anywhere but stay on this ring, right? So that's a simple example of a local constraint where not just the integral has to be a constant, but for every point on its trajectory, doesn't matter how the particle is moving, the particle has to be on that ring. So that's a local constraint, right? For every point on this for any time, basically. So we'll see how to deal with that. It's just a slight modification of this prescription, but still there are things to figure out, right? And so I'll talk briefly about that. I don't want to spend too much time. Hopefully by the end of next week, we'll get the chance to cover most of this, so that for the rest of the semester, we'll then talk about group theory. Okay? So we're supposed to talk about group theory, and what I'm going to do is I'm going to, in fact, use the chance. So group theory is often about discrete group theory, but I'm going to be a little bit rebellious and talk about continuous group theory, because I feel that for physics, for much of fundamental physics, continuous symmetry is quite important, and it's not well taught, at least my experience here at NCU. So that's my plan. And then on the way of our doing group theory, we will encounter some special functions as well. All these things are actually tied together, despite how it's being taught. So that's our game plan, right? So for now, let's take a 10-minute break, and then we'll resume with that maximizes entropy with fixed variance, fixed point function. So for your homework, you would actually work out the slight generalization of this. So as you know, the Gaussian doesn't need to be centered at 0, right? So here we have a Gaussian that's peaked at 0, but who says that's necessary, right? So we have now a Gaussian like that, but you can certainly easily generalize it by introducing yet another constraint. Instead of saying, so what we discover is that if you do not constrain x, but constrain x squared, then you get x equals to 0, the mean of x is 0. But if you now put in yet another constraint and demand that, in fact, your Gaussian has to be peaked at x naught, then you would get your hands well, try your hands on imposing yet another constraint, and then you will discover that this guy is nothing but the shifted version of this, right, as you may have expected. But it's good to, it will be good to see it for yourself, right? So square root 2 pi, sigma exponential of minus 1/2 x minus x naught squared over sigma squared. Right? That's what you will discover. Any questions for me? Okay, so next time, as I promised, we will start to do some Lagrangian mechanics. Again, some of this stuff you should probably have seen already in your classical mechanics course. Certainly by the time you are a senior undergraduate, either junior or senior undergraduate, at some point you should have seen Lagrangian mechanics and also Hamiltonian mechanics. Unfortunately, we're running out of time, so last time I taught this, the syllabus was a little bit different, so I actually went ahead also to teach Hamiltonian mechanics. Do you guys learn Hamiltonian mechanics? 一点点 Yeah.
没有讲太多。
Okay. You know what canonical transformations are? Yeah, probably not, right? Actually, for some reason, I also didn't learn it. So I taught myself Hamilton for some funny reason. I don't know why my classical mechanics courses didn't talk about Hamiltonians, but it is important because that's how you transition over to quantum mechanics, right? So the funny thing is that the way we learn quantum mechanics is we can't do it without first knowing classical mechanics, but yet quantum mechanics is supposed to be more fundamental. So there's this funny situation, at least in my view, where we are not. I think there's something that we're not understanding. Right? Otherwise, why is it that we have to teach classical physics before we teach